Okay, so this is going to be a rather short one. We're going to just cover the ideas of limits and continuity for functions of two variables, really just extending the ideas that we already know for single variable calculus, and just seeing how there's no real surprises in how these definitions apply to these kinds of functions, with a few little twists, okay? Okay, so here's the epsilon delta definition for continuity for a function of two variables. So a function of two variables with domain D, which is where D includes points that are arbitrarily close to AB, but not necessarily the point AB itself. We would say the limit of f of x as xy approaches AB, we say that limit is L, and we would write this as lim and then xy goes to AB, f of xy equals L. If for any epsilon greater than 0, any small number that someone desires, we can find a delta greater than 0, such that as long as xy is no more than delta away from AB in like distance, then f of xy is no more than epsilon away from L. It's the same idea, but just extending it to two variables. So here's the theorem about limits non-existing. If the function approaches L1 as xy approaches AB along one path, say path C1, and if f of xy approaches L2, some other limit value, as xy approaches AB along some other path, call it C2, if those L1 and L2 don't equal each other, then the limit of f of x as xy approaches AB, that limit does not exist. So the limit, the function has to approach the same value no matter along what path you take to get to AB. For example, let's take a look at this. The limit of x squared minus y squared over x squared plus y squared. If path C1 was, let's have y equal to 0 and x is just approaching 0, right? So this is like we're going along the x-axis. What this limit is going to be, we can find by, this is the limit as x approaches 0 of x squared over x squared. Well, that's just 1. If y is equal to 0 along this whole path, right? But along C2, if we say like x equals 0 and we let y go to 0 slowly, like along the y-axis, this is the limit as y goes to 0. It would be negative y squared over y squared. That would be negative 1. So in this case, the limit does not exist, because you can take two paths to get to the origin, and this function has two different limit values. So let's take a couple other examples. Let's look at this one. If with the limit here, let's take the first path be the x-axis. So let's say y equals 0 and x have that approach 0, right? So in this case, this is going to be the limit as x goes to 0 of, it would be 0 over x squared, right? And this function is going to be 0 everywhere, except for when x equals 0. Let's take another one. If we go along the y-axis, you'll see that we'll have, say, if x is 0 and y goes to 0, this is the limit as y is going to 0 of the function. It's still going to be 0 over y squared. That's still 0. So you may think, oh, okay, well, the limit's probably 0. But let's take another one. Let's go along the line x equals y. And so when we are going along the line x equals y, this is like where if we were to approach the diagonal or the origin from along that diagonal, what we'll have is this is the limit as, you can take your pick, x or y as your, let's say x goes to 0, y is going to be x. It's going to be x squared over, well, it would be 2x squared, right? Because x and y are equal along this path. Well, this is 1/2, which is not the same, so the limit does not exist, right? So you can see how by carefully choosing a path, you can find different limiting values and to show that a limit doesn't exist. All right, let's take another look at this example. This function, let's check, one way to check is to do some arbitrary diagonal. Let's take C1 to be, we're going to go along the diagonal line y equals mx. So for any diagonal slope you would want, except for a vertical slope, this is going to be the limit as x goes to 0. Right, as x goes to 0, y is going to go to the 0. But what I'm going to have, I'm going to write, on the numerator, we're going to have actually m squared. Well, I'll write it out in steps. We'll have x times mx squared over x squared plus mx to the 4th, which is, this is a limit as x goes to 0 of m squared x to the 3rd over x squared plus m to the 4th x to the 4th. What we'd have to do a little bit of kind of finagling with this to see what this limit is going to be, but you will notice as we take out the, if we factor out x to the 3rd, yeah, we can factor out so we can factor out an x squared from the denominator, would have 1 plus m to the 4th x to, squared now down there. And when you factor those out, you'll see we get the numerator, we're going to go to 0, and the denominator would actually go to 1. Oh, actually, it would go to, yeah, 1. So this is going to be a limit of 0, right? 0 divided by 1. However, if we were to take some other path where, let's say, we'll go along the path x equals y squared, okay? So then this limit is going to become the limit as, I'll say the limit as y goes to 0. And so we're going to have in the numerator x times x, and down below we'll have x squared plus, that becomes y squared is x, so y to the 4th is x squared. So this is going to be x times, this is the limit. Oh, let me, yeah, let's redo this in terms of y's. Okay, so we're going to replace the x's with y squared. So we'll have y squared times y squared over y squared squared to the 4th, right? Plus y to the 4th. So what we get here is, this is the limit as y goes to 0 of y to the 4th over 2y to the 4th. So this is just 1/2. So again, we have the limit is different from along different paths. So this is not, the limit does not exist. Now, how you find this, how you find the paths is kind of a bit of a trial and error kind of thing. So now continuity. So this is the same definition pretty much that we have for single variable calculus. We say a function of two variables is continuous at some point a, b if the limit as xy approaches ab is just equal to f of ab. And then we would say f is continuous on its domain if f is continuous at every point on its domain. So for example, polynomials with terms c x to the m y to the n, where c is some constant real number and m and n are non-negative integers. So these kinds of polynomials would all be continuous on all of R2. Also, rational functions are an example of functions that are continuous on their domain because they're a quotient of two rational functions, two polynomials. So everywhere on their domain. So except for any discontinuity points, right? Any points that aren't in the domain, they're not continuous there because they're not in the domain. But I'm saying they're continuous everywhere on their domain. That's the definition. So take a look at this example. F of xy is x squared minus y squared over x squared plus y squared. So this is going to be continuous. Well, the domain is all x and y, right? As long as x squared plus y squared isn't equal to 0. In other words, the only way that x squared plus y squared could be equal to 0 is xy has to be not equal to the point 0, 0. So it's continuous everywhere in its domain, and the domain is all of R2, R2 except for the point 0, 0. So if you take a look at this other function, now I've filled in the gap, so its domain is all real numbers, all of R2. But the question is the limit, is it what is the function approaching when xy is getting close to 0, 0, right? What is the limit as xy approaches 0, 0? So for this one, that you have to realize, like if you're approaching, let's say for example, y equals x, right? Then this function is going to be the limit as xy approaches 0, 0. This of f of x y is going to be the limit as, say, x goes to 0 of 3x to the third over 2x squared, right? And this is going to be 0. So this isn't enough to prove that the limit is 0 from along all curves. What we'd have to, we could suspect that the limit is 0. We can try to prove this using the epsilon delta definition. So let's give that a shot. Okay, so we're going to suppose suppose that we have some epsilon greater than 0, right? If we want some delta greater than 0, such that's going to imply that 3 times, that as long as we want the delta to be such that as long as as long as the xy is no farther away from 0 than delta, then this function, I should say, this function is no further away than epsilon away from 0, right? That's absolute value. Now, this right-hand side is actually, this is equivalent to saying 3x squared times absolute value of y over x squared plus y squared is less than epsilon. The only term that could possibly be negative would be that y, or the only kind of part of it, this only factor, the y, because everything else is squared. And so we can kind of rewrite this as 3x absolute value of y has to be less than epsilon times x squared plus y squared. Okay, we can observe that because x squared because it's the denominator here, x squared plus y squared is no smaller than the numerator. This x squared over x squared plus y squared, that's less than or equal to 1. And so we could make this chain of inequalities that 3x squared absolute value of y over x squared plus y squared is less than or equal to 3 times absolute value of y. Right, what I'm doing is I'm saying this part of the fraction is less than or equal to 1, which is the same as 3 times the square root of y squared, which is less than or equal to then to 3 times the square root of x squared plus y squared. X squared plus y squared is going to be no smaller than y squared, right? And if we want this to be less than epsilon, then what we can do is we can just we can just let delta be epsilon over 3. I'll show you what I mean. Okay, so given an epsilon greater than 0, we let delta be epsilon over 3. And so if as long as the square root of x squared plus y squared is less than epsilon over 3, then that's equivalent to 3 square root of x squared plus y squared is less than epsilon. And then we can build up that inequality to lead us to the fact that the absolute value of 3x squared y minus over x squared plus y squared is, well, this minus 0 business, less than epsilon. So the limit indeed is 0. So this function is a continuous function everywhere on R2. So that's our conclusion. F of x, y is continuous on all of R2. So we're not going to spend a ton of time looking at continuity. I just wanted to touch on these concepts, but we just want to have this kind of in the back of our minds as far when we talk about whether something is a continuous function of two variables. This is what we're talking about. All right, that's pretty much it for this section. We're not going to spend time really working on problems from this section, but we want to kind of be familiar with the concepts of this. All right, bye.